Okay, so chapter 16, we're going to be using what we used in chapter 15. So if you're not really comfortable with 15, go back and make sure that you have that down. You need to be able to find H plus concentration from pH, and you need to be able to find pH from H plus concentration, and possibly OH negative from POH and POH from pH, but especially the H plus and the pH. So what we're going to do though is apply that to weak acids and bases. So we pretty much focused on the strong acids and bases in chapter 15. Now we're going to focus on the weak acids and bases. We're going to start with simple acid-base equilibrium, those that react where a single acid or base reacts with water. We're going to look mainly at weak acids and weak bases. And we also are going to consider salt solutions because salts, some of the ions, so some weak acids and bases, their conjugates will be part of a salt, and they can also be weak acids or bases themselves. And so we're going to consider what that means. So let's first look at acid ionization or acid dissociation. It's the reaction of an acid when it's put into water. So this is something you're going to have to be able to do, is write these acid ionization equations out. So for example, acetic acid, when it's added into water, you get the following reaction, the following equilibrium set up. So again, you need to be like, if I said write the acid dissociation equation for acetic acid, you would write the acid HC2H3O2, add water to it, and then on the right hand side you need to be able to write the H3O plus, so the H plus has left the acetic acid and gone to the water to make H3O plus, and then what's left over is the acetate ion, the C2H3O2 negative. So like I said, one thing you need to be able to do is write an equilibrium for whatever acid I give you. So because the acetic acid is weak, we know that it only dissociates to a small extent. So that again is why we set up the equilibrium. We don't have the arrow going all the way to the right. We have, and we'll see later, only maybe about 5 or 6% of the acetic acid actually dissociates. So only a very small percent is in the ionic side of the equation, and probably the majority of it is on the left-hand side of the equation. So the important thing to remember about a weak acid or base is that the acid concentration itself, so let's say this acetic acid was 0.1 molar. We absolutely cannot know what the H plus ion concentration is because it doesn't dissociate. If it dissociated 100%, we would say, all right, then the H plus is also 0.1, the same as the acid. But in this case, because only a small percentage dissociates, we can't tell what that amount is by just looking at the equation. So we're going to have to do some calculations to figure that out. So this is the important thing. If you have a weak acid or base, you cannot know the H plus concentration without other information given to you. All right, so this is the other information. So for a weak acid, when we set up our equilibrium, now this is a generic monoprotic acid. So HA plus H2O gives us H3O plus A negative. Again, this is the basic setup for a weak acid. Write the acid plus water, and then on the right hand side you have the H3O plus the conjugate base, the A negative. It doesn't matter which order you write them in, the H3O plus or the A negative, whatever order. But remember that this is the acid dissociation equation. Then if we set up we can set up the equilibrium expression. Remember, products over reactants. And again, here's the reason why we usually don't include pure liquids, because they're actually a constant. So we saw that in the last chapter. The H2O, which shows up in the denominator, is, since most of the solution is water, it's pretty unchanging, and so we consider it a constant. So if we rewrite it, if we move it over to the left-hand side of the equation, we can see it like this. So we get rid of the H2O, and since the H2O is a constant and the Kc is a constant, we get a new constant which we're calling Ka. Ka stands for the acid ionization constant or the acid dissociation constant. So Ka equals H3O plus times A minus over HA. Ka is just a value that you can look up or is given to you in the problem. So here again is the expression. Ka is always equal to the products, H3O plus times A minus, the conjugate base, divided by the acid, the concentration of the acid. Just like we've seen before with equilibrium numbers, if Ka is a very large number, that means that products predominate, so the numerator predominates over the denominator, and that would indicate a stronger acid. So the bigger the Ka, the stronger the acid. The smaller the Ka, the bigger the denominator would be, or the more prevalence the denominator has, which means that very little has dissociated, and so a weak acid will have a small Ka. On the next slides, we'll see some values of Ka. So just a note, if you're doing a problem either on OWL or now if it's on a test, I would give you the Ka value, but sometimes the homework problems will assume that you're going to look it up. So if you don't know the Ka value, you might find it on this next chart. So here you can see some of the typical Ka values. There's acetic acid, 1.7 times 10 to the minus 5. Benzoic acid is very similar. Boric acid, you can see 5.9 times 10 to the minus 10th is a much weaker acid than either of the two above it because it has a much smaller Ka value. If an acid has more than one hydrogen that it can donate, they're going to do it each in one step. So when you write an H plus reaction, when you write an acid reaction in water, you're only ever going to give up one H plus, so it's going to happen in two steps. So actually, if we were writing it for H2CO3, we would have H2CO3 plus H2O gives us HCO3 negative plus H3O plus. And then we could actually have a second step where HCO3 negative plus H2O gives us CO3 negative 2 plus H3O. So each hydrogen has its own Ka value associated with it. And you might remember in chapter 15, we said that the second, once a hydrogen was removed, the acid was much weaker than if it had all the hydrogens. And you can see here then that the carbonic acid H2CO3 has a stronger Ka value or larger Ka value than the second one, which is much smaller. Although both of them are weaker than either acetic or benzoic acid. Anyway, you can look at some of these different values and you may need to use them at some point. And here's just some more. So you can see here oxalic acid has 2 hydrogens, so again it has 2 Ka values. Phosphoric acid, which has 3 different hydrogens that it can donate, actually has 3 Ka values. One thing you don't see on here are the very strong acids like HCl, HNO3. They all actually have such large Ka values where the numerator is nearly, well actually the denominator is nearly 0, which of course is impossible. You can't divide by 0, but it's approaching infinity, and so the Ka values are very, very large for those very strong acids. All right, the degree of ionization of a weak electrolyte is just how many molecules react to form ions. So in other words, what percentage of the molecules do dissociate? You can figure this out by using like a pH meter or some kind of measurement, but the main thing is we're going to learn how to calculate it from a problem. The pH is often going to be used to be able to determine the degree of ionization, as we'll see in some of the coming up problems. So let's look at an example. Nicotinic acid is a weak monoprotic acid with the formula HC6H4NO2. Again, remember, only the H on the front is acidic. A 0.012 molar solution of nicotinic acid has a pH of 3.39. Calculate the acid ionization constant for this acid. All right, so it's really important to note that because this is a weak acid, we know that H plus concentration cannot be equal to 0.012. It's going to be less than that because not all of the acid dissociates. So we can't figure it out just by looking at it. We're going to have to do something else. So if this were a strong acid, we'd be all finished because we would just say, okay, H plus equals the same as the acid, and so negative log or whatever. But in this case, an equilibrium is set up and less than 0.012 will actually dissociate. Just sometimes you don't have to do this. I probably, if you were just rewriting this, you would just write H, C6H4, NO2. Your book chooses to abbreviate the C6H4NO2 as NIC, and so just to make it a little bit easier to write. So the very first thing you want to always be able to do is write the equilibrium expression. So you write the acid plus water, and then on the right hand side you've got the H3O plus, because the HNIC gives up the H plus to H2O to make H3O plus, and then what do we have left over? We have the conjugate base NiC negative. We have to set up the equilibrium because again we don't know how much of the HNIC has actually dissociated. All right, now we did this back in chapter 14 with equilibrium. We can set up an ice chart, and we're going to let X be the moles of acid that dissociate. In other words, how much of the HNIC has actually broken apart. So we start with our ice chart, and we know that initially our HNIC concentration is 0.012. Some of it has dissociated. We're going to call that X. And so the amount of HNIC after equilibrium is established is 0.012 minus X. We also know that before equilibrium is established, we have no H3O plus and no NIC negative. But after equilibrium comes around, because they're all 1-to-1 ratio, the H3O plus concentration will also be X, and the NiC negative, the NIC negative concentration will also be X. Okay? So now we can plug this back into our Ka expression. So our equilibrium constant expression is H3O plus times NIC divided by HNIC. We can plug in what we just got from our ice chart, and we get X squared over 0.012 minus X equals Ka. So I just want to stop here for a second, because almost all of the problems that we're going to do will end up at this equation where you know the equilibrium expression and the Ka. In this case, we don't know the Ka, we're trying to find it. So for somehow, some other information in the problem is going to tell us what X is. But a lot of other problems will be the opposite, where we'll be given the Ka value and we need to find X. So I just want you to see this is a pivotal equation where if you know X, you can find Ka. If you know Ka, you can find X. And so you're going to use it both ways. In this case, we're looking for Ka. So somehow, some information is given in the problem that will tell us what X is. Okay, so let's keep going. What is that piece of information? It's the pH, because remember, what does pH tell us? pH tells us what H plus concentration is. All right, so pH is 3.39. So we can find out what is H plus concentration, or H3O plus is the inverse log of the negative pH, or the inverse of the negative pH. Sorry, inverse log of the negative pH. So anti-log negative 3.39, or in other words, 10 raised to the negative 3.39, gives us 0.00041 equal to H3O plus concentration, or 4.1 times 10 to the minus 4 molar. That's the concentration of the H plus. We know that because that's what pH tells us. pH tells us the H plus concentration. So we know in this case that the H plus concentration, we already defined that as X a couple slides ago. So H plus equals X equals 4.1 times 10 to the minus 4. Well, it's equal to X no matter where it shows up in that equation. So now we can plug X into that equation. So 0.012 minus X is equal to 0.012 minus 0.00041. What I want you to notice, this will come up in a little while, what I want you to notice is that to two significant figures in this case, we come back to 0.012. So what I want you to notice is that 0.00041 is very much smaller than 0.012, and so it becomes negligible in this case. It won't always do that, but it does come negligible. So this is something to remember in a little while. So basically, the amount of acid is virtually unchanged. Only a very small amount has dissociated. But that amount is important not so much when you subtract it from the original amount, but when it plugs into the equation. So let's plug the x into the equation. All right, so 0.00041 quantity squared divided by, and if you want to, you can plug in for x 0.00041. So you could use more significant figures and do the calculation. But to two significant figures, our value of Ka is 1.4 times 10 to the minus 5. Okay, so you can use this equation. You're going to get really good at setting up the Ka expression with x squared over the initial concentration minus x equals Ka. And like I said earlier, either you'll be given Ka and you have to solve for x, or you'll be given x by like the pH, something like that, and then find Ka, which is what we just did. All right, now it didn't ask for this, but let's decide what is the degree of dissociation, or the percent of dissociation, or degree of ionization. They all kind of mean the same thing. So the degree of dissociation just means how much of it has actually dissociated divided by the total amount that you have. And then to find the percent ionization, you just multiply by 100. So we know how much dissociated, so we can plug that in, divided by the total amount, 0.012, and then multiply that by 100. All right, so the degree of dissociation, 0.00041 divided by 0.012 is 0.034, which is 3.4%. So this acid only dissociates about 3.4% of the original. Only about 3.4% of the 0.012 actually dissociates. So again, you can see that we could not use the 0.012 to find our pH because only a very small percentage actually dissociates. Anyway, don't forget, degree of dissociation is just the amount dissociated. So what is the H plus divided by the total original concentration of the acid? And that gives you your percentage. Okay, so like I said earlier, once you know the value of Ka, you can actually calculate equilibrium concentrations of species, like what is the acid after equilibrium, what is the A minus after equilibrium, and what is the H3O plus. And then we'll also be able to find the pH by using the H3O plus, just like we did in chapter 15. All right, so what I want you again to note is that in the previous example, the degree of dissociation was so small that X was considered negligible when compared to the original concentration of the nicotinic acid. The reason why this is important is because it's going to give us a shortcut, or we'll be able to use a shortcut sometimes that will help us solve these problems quicker without using the quadratic equation. So I just wanted you to note that, and we'll see when we can ignore the X and when we can't. So it's the small value of the degree of ionization that allows us to ignore X when we do an equation, which you'll see in the next example. Now, it's going to depend on the degree of ionization depends on what the acid is, what the concentration is, and what the Ka is. And so we can actually predict whether we can ignore the X or not. So when can we use this simplifying assumption? When can we assume that X is going to be so much smaller than the concentration of the acid that we can ignore it and not use this quadratic equation? And again, I'm going to do an example in just a minute to explain what I'm talking about. Well, it turns out that if you take the concentration of the acid that's generally given in the problem, divided by the Ka, which is either given to you or you can look up, if that number is greater than 100, what that means is that X, or the amount of H plus ion concentration that's around, will be so much less than the original acid concentration that it will be negligible. Now, obviously, for if you used 100 significant figures, it wouldn't be. But what they're saying is, in terms of significant figures, the X is so much smaller that when you subtract it and then you round back to use the correct number of significant figures, you won't see any difference. So another way to look at it is if the percent ionization is less than 5% of the original, then usually we can make this assumption to make it easier. Now, if you can't, what happens if this is not true? Well, then you're just going to have to use the quadratic, which is not the end of the world, but we're just going to try to make this as simple as possible as we do it. All right, so if either of these are true, either 5% dissociation, which usually you can't figure out till you've done the problem. So the easier one is to use the CA over KA. If CA over KA is greater than 100, what we're going to do is we're going to ignore X. I want to be really clear, though, that when you're working these problems, you should note that in your problem. You should say, because CA over KA is greater than 100, we're going to ignore X and simplify this equation, or something to that effect, so that you're making, so that your math is at least correct, that you're showing what assumptions you're making along the way. And again, if this simplifying assumption is not valid, what that means is you're going to have to solve for the quadratic equation. And we've had a little bit of experience with that in chapter 14, so hopefully this is not anything too new for you. Okay, so calculate the pH of a 0.30 molar solution of acetic acid. So the first thing you should always do is go ahead and write your acid equilibrium. If you know it's a weak acid, write the acid equilibrium equation. So here we have acetic acid plus water gives us H3O plus C2H3O2 negative. The next thing you probably want to do, well, the next thing you should do is write the Ka expression. So Ka equals products over reactants, but we omit the H2O. So H3O plus concentration times acetate ion concentration divided by the acetic acid. Now, in this kind of problem, because you're trying to find the pH, you need to know what the Ka value is. Either it's given to you in the problem or you have to look it up on the chart. It turns out that Ka for acetic acid is 1.7 times 10 to the minus 5. It was on the chart a few slides ago. So we can use that value. The next thing you want to do is create your ice chart. Create the table to express the concentrations in the reaction. So again, your initial concentration of your acid is 0.3. Your H3O plus is 0 because it has not come to equilibrium yet. Your C2H3O2 negative is also 0 because the reaction hasn't occurred yet. During the reaction, some of the acetic acid will break apart. We're going to call that amount X. The good thing is that if one acetic acid breaks apart, we get one H3O plus and one acetate ion. And so if X breaks apart, then we get X H3O plus and we get X acetate ion. So they're all one X's. And this is the really nice thing about this chapter, acids and bases, is that all the reactions are 1-to-1. So your stoichiometry or your X's are always, everything's to the first power and everything's 1X. So that makes it a lot easier. Okay, so at equilibrium, the concentration of acid is 0.3 minus whatever has dissociated. The H3O plus is the same as X, and the acetate is X. So now we can plug those equilibrium values into our Ka expression. So 1.7 times 10 to the minus 5 equals X squared over 0.3 minus X. Now, we could solve this very easily for X because it's one equation and one unknown. However, you notice that the way it is, you're going to end up with the quadratic equation. What would you do? You would have to take the 1.7 times 10 to the minus 5, distribute it times 0.3 minus X equals X squared. But remember our simplifying calculation first. We're going to see if it will work by using the guidelines that we talked about earlier. So what do? We take Ca over Ka. Ca is 0.3, concentration of the acid, divided by Ka, 1.7 times 10 to the minus 5th. If you calculate that, you get somewhere around 17,000. Clearly that's greater than 100. So what that means is we can assume X is negligible compared to 0.3. And don't forget what I said, you want to write somewhere. So if you write the Ka expression, you get the Ka equals X squared over 0.3 minus X. And then in your next step, you might say, because Ca over Ka is greater than 100, we're going to assume X is negligible compared to 0.3. So what does that do? Now you can ignore the minus X in your expression. Now you can't ignore the x on the top, because if you multiply by a very small number, then it's still very significant, but it's not significant when subtracting it from a number that's much bigger than it. So we're able to, since x is much less than 0.3, we can ignore it in the denominator. Now we have a very simple equation to solve. So if you multiply both sides by 0.3, you get 5.1 times 10 to the minus 6 equals x squared. And then if you take the square root of both sides, you get x equals to 2.3 times 10 to the minus 3, 0.0023. And it's, if you were telling me concentration, you would use molar. So since x equals H plus, then we can find the pH. It's the negative log of 2.3 times 10 to the minus 3, which is 2.65. So we can find our pH. All right, now we already used our simplifying assumption, which is a good enough reason, as long as you explain it at some point during the problem why you did it or how you came across. You can use it. But let's just check ourselves to see if that 0.3 is negligible. And in fact, if you take the x, 2.3 times 10 to the minus 3, divide it by the 0.3, our initial concentration, we're going to get, times 100%, we're going to get the percent ionization, which is 0.77%. So yes, it's clearly much less than 5%. And so, and you can also just do like a visual, 0.30 minus 0.0023. If you round that back to two digits, 2 decimal places, you're going to get back to 0.3. So it is negligible compared to that. So if it's less than 5%, we can assume that x is much less than 0.3, or if we do the subtraction, we can see that as well. Now, that doesn't mean you couldn't use the quadratic equation. You could always use the quadratic equation. The thing is, it would have given you the same answer, and it would not have been significantly different from the answer we got, and it would have taken you a whole lot more time to do it. So you can always do the quadratic equation. You can just use this simplification if you want to, but do note it when you do use it. Okay, again, just to compare, what would the pH of a strong acid of concentration 0.3 be? So, for example, what would the pH of a 0.3 molar HCl solution? Well, because HCl is considered a strong acid, it completely dissociates, so we know that the H plus concentration will be the same as 0.3 because it completely dissociates 100%. So we know that H plus is 0.3. So what is the negative log of 0.3? It's 0.52. So note that the pH of a weaker acid of the same concentration should be quite a bit less than a strong acid. So the pH of a weak acid is higher than that of a strong acid of the same concentration. This is because the strong acid completely ionizes, completely dissociates, and so it has a higher H plus concentration. So don't forget, the stronger the acid, the larger the Ka, the lower the pH, if they're all the same concentration. All right, so what is the pH of a solution obtained by dissolving 0.325 grams of acetylsalicylic acid, which is aspirin, there's the formula, HC9H7O4, in 0.5 liters of water? The Ka for acetylsalicylic acid is 3.3 times 10 to the minus 4th. The 25 degrees is not really important. It's just that the Ka value is given at that temperature, and so they're just being complete with this problem, but we're not doing anything with the temperature. The first thing that I always want to do when I'm working a problem is to write the equilibrium expression. So there's our acetylsalicylic acid in water, giving us H3O plus the acetylsalicylate ion, C9H7O4 negative. A couple of other things, we don't know the concentration of the acid in this problem, so we're going to have to figure it out. So we can find the molar mass of acetylsalicylic acid is 180.2. And then we can find the concentration of the acid. All right, so 0.325 grams is 1.8 times 10 to the minus 3 moles. And then 0.00180 moles, 1.8 times 10 to the minus 3 moles, divided by a half a liter, 0.5 liter is 0.0036 molar. So we had to do a little bit to keep our, to get our initial concentration. Just note that they're wanting you to keep only 2 significant figures because we only know 2 significant figures for Ka. It's not critical, but at the end you probably want to round to 2 significant figures. All right, so just take a little note here. Now we know what Ca is and we know what Ka is. And if we do the division, what you come up with is 11. So notice that Ka 0.00033 and Ca 0.0036 are really actually too close for X to be negligible. So right away we know that we're going to have to solve the quadratic equation. So that's a good thing to know right from the start. So we're prepared. So we have to solve the quadratic equation. All right, so let's cite up our ice chart. The first thing we'll do is remember let X be the amount of acid that dissociates, so it's also equal to H3O plus formed, and then the amount of acid that dissociates will be 0.0036 minus X. So let's look at the chart. All right, so there's our ice chart. So 0.0036 initial minus X, 0.0036 minus X. And what we're trying to find, remember, what's our goal? We're trying to find the pH. Well, if we find out what X is, that will tell us what H3O plus is. And if we know H3O plus, we can find pH. It's important to note that we cannot, X is not negligible compared to 0.0036. All right, so now we have our ice chart, so we can plug these into our equilibrium expression. So H3O plus times C9H7O4 negative over HC9H7O4 equals Ka. We know what Ka is, 3.3 times 10 to the minus 4th, so we plug in our values. And then here's our expression, X squared over 0.0036 minus X equals 3.3 times 10 to the minus 4th. But now we need to get it in the correct format to use the quadratic expression. So we rearrange it. First of all, multiply both sides by 0.0036 minus X. Don't forget that you have to distribute. So multiply 3.3 times 10 to the minus 4th times 0.0036, and we get 1.2 times 10 to the minus 6. And then 3.3 times 10 to the minus 4th times negative X gives us minus 3.3 times 10 to the minus 4th X. So now if we just rearrange and put all of them on one side of the equation, we get X squared plus 3.3 times 10 to the minus 4th X minus 1.2 times 10 to the minus 6 equals 0. So now we have it in our correct form, and we know that A equals 1, B equals 3.3 times 10 to the minus 4, and C equals negative 1.2 times 10 to the minus 6. So if we plug that in the quadratic equation, X squared equals minus B plus or minus the square root of B squared minus 4AC over 2A. Plug in A, B, and C, and we get X equals 9.4 times 10 to the minus 4th and negative 1.3 times 10 to the minus 3. Now we can ignore the negative root because there's no such thing as a negative concentration, and so we're just going to go with the X equals 9.4 times 10 to the minus 4 molar, and that equals H plus. So X equals H3O plus equals 9.4 times 10 to the minus 4th molar, and we can calculate the pH. The pH is negative log of 9.4 times 10 to the minus 4th, which is 3.03. And just note that X is not insignificantly smaller than the original concentration of 0.0036. So we cannot ignore that. We cannot ignore X when compared to 0.0036 because this is pretty close to the same value. So that is how we do it.